and when it's up in the right hand corner, it means that it's closed. That's it. Of course, when it's open and it's grounded itself more than anything else. So, and it's going to show you another picture we have over here. We talked about as far as working with the in starting the controller. These are the starting procedures and everything else for this controller. You energize the equipment, starting like it says main devices, then feeders and so forth. You move the to the open or the ungrounded position, then you close the IM, which is once again the isolating means. Then you press the run start button located on the operator panel, which in turn would close your contact area. So everything goes in a certain sequence. The same thing here, when you stop it, located on the operator panel, you look through the to verify that the contactor is open. And it says indicator arm repositioned on the green side of the label. If the access is required within the medium voltage compartment, or maintenance of downstream devices required, you open or ground the IM. So once again, you got to go through that process of opening it. Inspect the equipment to determine, and we talked about that yesterday a little bit, as far as the environment, or whatever your environment is, whether it's the ideal, normal, or harsh environment. And that, determines at what intervals you will inspect, do the PM. Because you can inspect the equipment at any given time. It's the PM that's going to amount to a schedule that you guys will set up. We do have recommended inspection on the maintenance, and it's generally a year. This is what you want to inspect for. Okay. Symptoms of overheating is one of the things that heat is the #1 enemy of any kind of equipment, whether it's electrical or mechanical. When heat is introduced to two pieces of metal, or this when they're rubbing together, we call that friction. I know those are moving parts. Well, in electricity, the actual flow of electricity is what causes the friction, and this causes the heating of the conductors and components and stuff like that. But regardless, heat is the enemy of semiconductors as well. They break down because of the heat. So you have thermal breakdown in electrical equipment and everything else, including conductors. And conductors, you can, especially if it has a loose connection. Here's where your infrared, when it comes to PMs, so when you do an inspection, you can go around with an infrared gun and shoot stuff and everything else to see if you got any hot spots. And plus, if you have a history, or if people maintain a history of the PM that they might do, let's say for example you have a motor that for whatever reason keeps tripping out. There's a reason that motor's tripping out. Either the circuitry in it is wrong, the settings on the breaker are wrong, the wiring size is wrong, the motor itself, the armature, something within the motor is wrong to cause it to keep tripping. Because if everything is good, as far as, okay, the wire is correct, the size of the breaker is correct, the setting on the breaker is correct, yet the motor is, for whatever reason, it's got a nameplate data on there, and it's got a rate. If you put an ammeter on it and it's drawing more amps than it's designed to, something is wrong with the motor then at that point, and not any of the other equipment. But those are the factors when it comes to troubleshooting, especially what you were talking about, troubleshooting stuff. You have to determine and say, okay, hey, is all this other stuff good? So you isolate the motor at that point, the same. Or the first thing you might do is go ahead and put the ammeter instead of checking all the other stuff, and then say, okay, am I drawing too much current? So you figure out if the motor itself is the cause, and then if the motor is not, then you can start troubleshooting and saying, okay, do I have enough wiring, or is the wiring correct, or is my settings correct? If these have been commissioned properly, and the settings on the breakers have been set properly by, it's called a coordination study. It's supposed to be done by a professional engineer, electrical engineer. Those settings are taken into account. They have a formula. They're the ones that do that. And of course, if they've done that coordination study for the settings for the breakers, then at that point also they have those numbers already that they can actually do the arc flash analysis for you. So therefore, it would behoove the utility to take those same numbers, go back to that same engineer, somebody like that, and say, look, give us an arc flash analysis now, or something like that. And it probably would be maybe a little bit cheaper because he already has that number. He doesn't have to figure out how many conductors there, the length of the runs. He's already done that when he did as far as with the setting for the breakers and so forth. So it should be a little bit easier, or a little bit cheaper than this, to get that arc flash analysis that helps you guys out when you go out there. And that arc flash analysis is going to tell you the category of PPE that you require, or the protection, how much protection do you require to work on this equipment when it's energized, or if you're going to do any kind of switching on this equipment. So that's the whole thing that you need to take into account when you start, doing this work and stuff like that. It's gotten very, with the FPA 70E, it's safe conscious more than else. People have gotten hurt so much in the industry and everything that they're looking at areas and finding out where the exact cause of these problems are at. And it has to do with people not being educated, and I use the word ignorant, not meaning that people are stupid or dumb. Ignorant means not knowing. And that's the whole thing, that the industry as a whole is really ignorant when it comes to the customer, because they do not realize the dangers and the potential that are there, because we're used to the things that we used to do. You know what I mean? It's old school and stuff like the other. You got this old generation of thinking that wasn't so much safety driven as it was more getting the system running driven, staying online or getting energized and stuff like that. In the process, though, we found there's a lot of mistakes that were made, for one thing, and there was a lot of things that could be done to actually make it even safer for people and still be able to work on equipment that is energized. And there's products that they come up with and stuff like that that make everything a little bit easier to work with. But you have to know and understand what's going on. This tightness and damage, this is what I was talking about, loose connections will cause it to overheat. Okay? And you always, like I said, you manually want to operate anything. Whether, I don't care whether it's a 20 amp breaker or a 100 amp disconnect or whatever it is, you manually want to operate those during your PMs, your periodics, shutdown, something like that or the other. When something faults or a breaker trips, and you might have other devices downstream, you want to isolate from the very first isolation means kill everything downstream. Once you've isolated, I'll show you that here in a minute, the maintenance, because we're getting right into it. When a fault occurs, a breaker trips, even on an overload, or any device opens up. Yes. Just for the sake of like a one-line diagram. Utility comes in to a transformer, ties into comes into a switch, like a high voltage HVL that we're going to cover here a little bit, and that's exactly what this is, more or less, like an HVL switch, that in turn can feed a certain amount to a common point, and that's where we have those motor control centers that we just were talking about right now. That in essence also, again, a disconnecting means on one end there, you're going to have a whole bunch of them. This one in turn now feeds another line somewhere else, or feeds more than one. Okay, let's say this goes to another HVL down over here, several HVLs. These in turn feed other transformers that are going to go down to your 480, and now you're going to have a breaker that's a main that now feeds other breakers, and that in turn would come back over here, now feeds MCCs that of course are going to be three phase and everything else, and you're going to have more loads here now that actually go downstream and keep going further and further downstream. Okay? So depending, and it makes no difference where we're at in this scenario. Let's go to the low voltage side to make it a little bit simple, you know. But because this is not a breaker, this is a breaker. These are switches, so switches really will not trip. You have to manually open them, okay? That's what you have to understand. This, of course, might trip open, or this contactor might drop out because of a problem or something like that or the other, okay? So it won't necessarily trip as much as it will drop out. Make sense?
You got bad cold or...
Right, exactly. Or the contacts for whatever reason, something, or whatever is supposed to help, because you're probably going to have permissives in here as well that are going to be required first, and then they're going to be more or less like little, also more contacts in between here and everything else. For whatever reason, it could be an interlock switch. It's got a little micro switch and everything else that allows the voltage to make the contactor close and stuff like that. That isolate means, excuse me, to be able to close that contactor and everything else, right? So once again, these are all switches compared to a breaker. Now the breaker is the one that I actually wanted to get to, because in essence it comes out, the way of thinking of it is the same regardless. You don't want to open this puppy up when all of these are all closed. They should have been opened. Maybe this going down to a lighting panel, something like that, you don't open your lighting panel, something like that. But if it's a motor or something like that or the other, you definitely want to open the motor and stuff like that. Especially if it's got a disconnect or something like that or the other, because we can go from here and actually take this down to a three-phase, oops, well actually it should have been like, you know, more or less 3 phases for the motor and everything as far as the disconnect. And you know, it's going to be tied in actually to the motor itself. Now it's where the motor is running and stuff like that, right? Okay. This breaker, or these breakers, are designed to open, like I said, on a fault. They're not designed to close on a fault. So if this breaker, or any one of these breakers, let's say this one opens up or this, what I would do to troubleshoot, I would immediately open all of these breakers right there, okay? And depending on what the fault was, or the trip indication of this, there's a breaker out here that's a P-frame type breaker, and it has a power logic trip unit in it, okay? And it has 4 LEDs on it. You'll see it out there. You'll be able to see the 4 little LEDs like this. And it has a reset button, and it'll say reset on it. This one is for the overloads. This second one is for the instantaneous and short circuit. The third one is for the ground fault. And the fourth one is an AP light. These two, and it would be on something like this, because it's going to be feeding motor control center. And these would be your other loads in your motor control center and everything else. Okay, so that's your main to that motor control center or whatever. Okay? That breaker trips, and you have one of these indications. And once again, maybe you don't have these indications, but regardless, the breaker is tripped. If a breaker is tripped and you don't know why it tripped, because you don't have any kind of indications, you do want to definitely isolate your loads before you try to close that breaker.
Yeah, you open everything in the panel and then bring your main back up.
If it'll stay on right to find it, exactly.
And then bring them up one at a time.
Exactly, exactly. And that's the right. That's the. But however, when you're doing that, you should be wearing your proper PPE, because in the event that this son of a gun here, for whatever reason, is shorted to ground.
Right.
Okay. When you go to close this, you're closing in on that fault.
Right.
That's why it's dangerous just to, just to go up there and start closing stuff or opening this. You don't know. What you got to keep in mind on something even down this far down the line. That's why those arc flash analyses are very important and stuff like that. The other is, okay, what is the potential there? Is the potential the same thing that we just saw in there? I always try, and that's the reason I show you those pictures, for you to have that picture in your mind constantly and saying, that's the potential, that's the kind of danger that I'm putting myself in front of.
You look for the worst possible scenario.
Exactly. And that's why you cover yourself, or you protect yourself for the worst case scenario. So let's say this, and once again, if you haven't had NFPA 70E training that tells you, and they actually show you how to do those calculations and so forth, that's why I can't get into that, because this is not an assembly class. But they'll show you how to do those calculations to find out, okay, so you do your own arc flash analysis, because what you'll do is you'll take the rating of the primary source that's feeding that breaker, then that breaker as far as the rating, the seconds that it clears, this, that, or the other, and then the number of conductors. You'd have to probably guess that or something like that if you don't know, but you could use your prints, and your prints would tell you you have so many cables and such a length and so forth, blah, blah, blah. They go from here to the transformer, something like that, that's feeding, that's a primary of that breaker, and as far as the secondary is concerned and so forth as well. What's the clearing device? Is it cable or is it bus run? Is it open air? So it asks all kinds of questions that you take into consideration, and then it'll come up with a number or the calculation as far as the calories. And when it comes to the calories, then there's also a list or a chart that says, okay, for this many amount of calories, this is the amount of protection that's required. If it exceeds the amount of protection that is available, then you cannot safely close these over here. Okay? At that point, if anything else, you're going to have to open this puppy up over here, or whichever, this one right here. You'd have to open that up. You're not going to know at that point. You see what I'm getting at?
Yeah.
Because if you exceed the protection, if the potential exceeds the protection that you're wearing, you're placing yourself in a position of hurting yourself. And that's basically all I really want y'all to do and understand, is that even though that's a good practice as far as troubleshooting, you have to know what your potential is there. If the potential is nothing or it's minimal, something like that, okay, not a big deal. But if it's not, that's I can't stress that enough. That you're placing yourself, especially when you go out in your t-shirts like that, and that's kind of where that we work, on a daily basis. And we don't stop to think about when we're going out there, you're doing your job and they call you out and say, hey, breaker tripped and everything else, go reset it, so like the other. Your mind's not on that, and you're wearing this or something like the other. You've got to think about that. I can't stress that enough. You have to stop and say, okay, well, wait a minute. Keep your mind on the job that you're doing. Forget about where you were at. Now you got a different task, and you got to dedicate your mind completely on that task now, and start looking at it from, you wear that hat now, turn it around, because you're no longer what can I say? You were doing something else over here. Now you got to be that qualified personnel that's working on this test equipment and everything else, or this equipment and stuff. Okay, and that's the procedure. The process is the same for every piece of equipment, like I was telling you. It makes no difference what the process is the same. It's going to be the same when you go doing your troubleshooting. You're not going to close this without all this stuff being open and everything else over here, because that's going to be under load. And the minute you put under load, what if one of these down over here has got a short in it, and you close these and then that short's going to come right there's where that short's actually at now. The fault, it's waiting for that potential. Two different potentials, all of a sudden you got that high potential, and then you got that ground coming on there, and just, you've got not that arcing over there, but you'll actually have that blowout on that side of the deal and everything. That's what you got to remember. It's all it's waiting for. That's just a direct path. So no matter how small, whenever that path is made there, it's going to take it all the way up to that high voltage, period. And it's just waiting for that. I mean, it doesn't seem like it, but it is. That's all it takes. It's all it takes. Something from way down. Lighting ballasts have caused fuses to be blown on utility poles that go back that far. And that's what I was talking about. Why? How come one of these didn't open up? It's one of those things that it just didn't. But it just took that one little fuse over here, or that ballast, 277, go back all the way to the utility to blow their fuses. And those are the ones that the guys that would close 2 or 3 times and stuff, and actually hurt and kill people trying to reclose because they, all the time. So for those fuses to blow, everything was perfect. That's sort of that triangle I was talking about. Everything started adding up, and then got right up to it, and bingo, there's when the accident happened. Because all that stuff was already on its way for it, and all it took was that one little ground to come there, and it took it all out. Stuff happens, gentlemen. And that's what I'm trying to get y'all to when you start working and stuff, to get in that frame of mind to think about what you're doing. It's not your everyday. We do it every day, and that's the problem, because we do it all the time. Repetitious. The word that's used a lot is complacent, and we do get complacent because we thought, I've done it over and over. It's never happened. And then one time said, well, since it's never happened, you're in a hurry now because you're trying to get home. It's your daughter's birthday or something like that or the other, or you've got a doctor's appointment or something that you're going to have to do, and your mind's on that doctor's appointment, and you forget and say, oh, I don't really need to put the suit on. It's never happened. This or the other. Next thing you know it, bingo. Or instead of using an insulated screwdriver, you use a normal screwdriver, and it slips, and you short out in between. The electrician here shared yesterday, as far as him being involved in it, where it wasn't the fuse clip itself that he did it on A phase, but they were so close together as far as the other one, the other group, that the A phase of the one clip pushed far enough to touch the C phase of the other one, and caused it, that incident stuff. Those little things. I mean, it's just those little things I'm saying that we get right to it to get us right to that point right there. Because we're just not watching it. This is a typical schematic for this, and it's in the book and everything else. And this is what I was talking about. You can actually go in there. Here's going to be your contactor, but you see how you got these these little arrows that you see right there. All it's telling you is that contactor is out of that block right there. These are those connections for that contactor when it gets inside. So this is in between. The contactor is in here, so you could take it out of there, like I was telling you, and you could actually troubleshoot it to try to find out, if it'll close or not. Okay? It's not that difficult. These are the interlocks. Let's see. So you can go through these test points, because this will be out as far as the contactor is concerned. That'll be with the contactor. And it's not that difficult at all, gentlemen. Believe it or not. I know it can look intimidating, but it's not. It's just follow it one line at a time, and you'll be able to figure this thing out easily. Troubleshooting wise. If the contactor, for whatever reason, doesn't close, you could actually take it out, like I said, apply external power to it, and then it should work. And if it doesn't, then you got to figure out, okay, why didn't it? And that's when you go to all these points and find out, okay, do I have continuity from here to here, like my connection wise, here to there? Right here, did this close? Did this contact actually, auxiliary contact, close, or is it made or not? That's going to provide that power to it. And that's what you're looking at, because these contacts are part of this contact. That's what it's shown by these little arrows here that I was telling you about. When you remove that, you're actually removing that in there. Okay? So that's when you check that, you're going to make sure that these actually open and close. So if that opens and closes, and when that contactor makes, that means that this is okay. Something else is wrong. And this is a full voltage reversing controller. That's the troubleshooting for this motor control center. For the mechanism, contactor, cannot close the contactor electrically. And here what we were talking about. Verify that the isolated means is closed. Isolated means access port is closed. Loose terminal connections. Loose plug connector in the low voltage compartment. Check the coil circuit. Check the control fuses. Electrical interlocks. And of course it says see equipment drawings. Check the linkage to the contactor and the contactor interlock and the arm assembly on the contactor for binding or hanging. So you have all of these, like I was telling you before, then I was saying, that's what I meant by these interlocks. When I pointed out over here, I said this is all I was talking about right here, because this stuff happens. And I know it happens, and that's where the majority of the time. And it could be, like I said, in the coil circuit itself. Because there's going to be permissives in the coil circuit as well. Okay. Let's get rid of that one. The next thing that we had on here was that multi-lin 269. Now the multi-lin 269, if you go to your page that you should be concerned with, this actually says section 3.2.
section 2?
Yes, well, it's divided to that you're looking at.
Divider 2?
Correct. But in the actual page numbering, it's section 3. You see the numbers 3?
Okay.
Which is page 3-1. And that's essentially where, I'm actually page 3-2 in your book.
Okay.
But that's what the,
That's what the multi-line looks
this is what the multi-line looks like, right? And I could spend a lot of time on this, which we don't have. But for you to operate this thing, you have the actual equipment here that you can actually read. And you can actually have the book in front of you when you're in front of that multi-line. And just step for step, instead of, like I said, I'm not going to read everything in this slide, but you have the same thing right here. If you look on page 3-2, look what it says there as far as actual values. It says description, it says function, right?
Mm-hmm.
Then you look a little bit further down and it says use. That's the use of that key. It can be pressed at any time, in any mode, to view actual. That's why it says actual values, okay? And it also, to go from page to page, you use the page keys. To go from line to line, you use the line keys. So using that and looking over here on page 3-1, you can see what it's talking about. You have your actual values, you have your set points, you have help, reset, clear, and store. So in all of these pages afterwards, it's going to explain, if you look just a little bit further down that same page on page 3-2, you're going to see the set points button, right? You look at the bottom of that set points button, and it tells you the use for the set points button. It can be pressed at any time, in any mode, to view or alter relay set points. And of course now again it repeats, you use the page and use the line, blah, blah, to go up and down. All set point increments are decrements to predetermined limits. When the desired value is reached, you use the store button. So you see, you use that, then you use your down arrow keys, and then you hit your store button, which would be more or less like your enter button. And now you've stored your values. The most important thing here that you should try to figure out or learn when it comes to this is the actual menus.